Hello and welcome to my new video. This is starting a new series summarizing modeling work from the past 20 years. Why did I start with modeling 20 years ago? I was fascinated by the illustrative possibilities and by the possibility of reconstructing biological structures using mathematical approaches. With this series, I will present you my results. For a start, today, I will demonstrate how to model simple thread-like structures. This is not particularly difficult, for sure, but these thread-like structures provide the basis for some of the more complex structures in the background. Which program did I use for my works? By pure chance, I started with the ray tracer Porphyry, and by pure chance, this was, back then, the program with the best scripting possibilities for low budget, at least as far as I know. This is a screenshot of a session showing the menu, part of a typical script, and the rendered image of a worm-like structure. I suppose nowadays most programs will allow to use scripts. Therefore, I will keep this presentation on a very general level without focusing too much on Porphyry. Metaballs are my favorite modeling tool, and I shortly want to introduce this approach. These are simply balls with increasing densities from the outside to the center. The surface of these balls can be rendered at any given density limit. This is boring as a single ball of course, but you can combine as much of them as you want. In combinations, densities are either added, as here, or subtracted, resulting in smooth biological surfaces. How am I producing my illustrations? It's always the same three steps. First, you have to define positions, where to place the metaballs and store them, example given in an array. The first step is the most complicated one, and we will almost exclusively deal with this step here. After all positions have been defined, metaballs will be placed at their positions in the second step. The resulting structure still has to be colored and textured, which does happen in the third step. Step 2 and 3 are differing depending on the actual software used, therefore we will focus in most cases on step 1. Okay, let's start. How can we define the positions for this worm-like structure just shown? We are working stepwise in a loop, adding a new element in each step. This at least partially simulates growth of such a structure. Since we want to work with a loop, we have to define a set of steps we can reuse in each of the 9 loops necessary. We start with only 2 dimensions. Here is a chain of 5 elements in the xy plane. All elements have the same distance to each other, but different angles with respect to the x-axis. We could produce these angles by simply using random numbers, but this would not look very natural. Random variation should not refer to the x-axis, but to the angle of the precursor element. What does this mean? Here I noted these precursor angles. We have to apply our changes with respect to these angles, for example like this. The angle of rotation is always a result of adding the precursor angle and the random angle. To have these precursor angles available, we have to store them in each loop. In Porphyry, this is done in an array. And how do we obtain our random angles? By applying random numbers to an arbitrary angular sector. The larger this sector, the more labyrinthine our chain. When adding this random angle to the precursor angle, we obtain our new angle of rotation. We have to store this new angle for being able to use him as a precursor angle for the next element, and we have to apply this angle for a rotation around the z-axis. So we start with a position on the x-axis in the distance d from the origin and rotate this position first around the z-axis and then, using an angle determined in a similar way, around the y-axis. This way we arrive at our new random position, which still has to be placed to the top of the growing chain. How is this done? Similar to the angle, simply by adding our new random position to the precursor position. This means also in this case we have to store all the positions, but this has to be done anyway since we want to fill them with metaballs in a later step. So let's summarize the steps of one loop. First, you have to determine random angles for the rotation around the z and the y-axis. You have to add these angles to the precursor angles, store them, and apply them for creating a new random position. Then, in the final step, you have to add this random position to the precursor position and store this new position as well. After repeating this loop 9 times, you have to find all the positions from our little worm. This way we obtain a slightly folded linear chain, as you can see here. To the very right, positions were filled with metaballs. They were scaled sufficiently large so they almost completely merged, and then they were textured. By modifying the scaling of the metaballs used, we can modify the final structure. The upper part of this picture shows a flat worm made of flat metaballs. The lower structure uses metaballs with a maximum radius in the center of the worm. Apart from metaballs, other objects are also possible. We can place completely different things on our positions, like these cells are used for depicting the Cyanobacterium anabina. I also want to show you a second, more elegant approach for defining somewhat longer threads. I have often used this approach in the form of a macro, allowing the integration of these threads into more complex structures. Here we first have to choose a starting and a final point for our thread. Then we have to select the number of sub-items and the range of variation perpendicular to the axis of starting and final point. These sub-items are determined in similar loops as the one outlined above using random numbers. Array provides an object spline connecting the points defined this way by smooth Bézier-like curves, allowing to calculate as many intermediate positions as necessary. By placing metaballs onto these positions at a sufficient density, you obtain nice smooth threads. And what can we do with such threads? We can use them, for example, for root systems like this one here. As I will show in a later video, with a macro for threads, we only have to combine such macros the right way to produce such a system. Well then, that's it for today. What about the level of detail in this video? Am I too superficial or too detailed? Just tell me, I'm keen to know. Otherwise, have a look at my next video, which will be about curved linear structures, about snail shells.